Welcome to the LEAP-1B. The LEAP-1B gives its thrust to the 737 MAX family of aircraft. In this document, you'll find pilot-oriented operational explanations and tips to familiarize yourself with this new engine. Let's begin with a short technical review. Fuel burn. The B737 MAX has been designed to reach a close to minus 15% fuel burn compared to the NG family. This target has been achieved thanks to design improvements made to the airframe, but most of it is due to a new generation of engines, the LEAP-1B family. On top of that, NOx emissions have been lowered by 50% and the noise footprint reduced by 75%. From the outside of the aircraft, the LEAP-1B is bigger than a CFM56-7B. The jet intake is 1.76 meters wide, which is 20 centimeters bigger than the one on the CFM56-7B. The ground clearance is 43 centimeters, which is compliant with all the certification rules, and does not induce any limitations in bank angle for landing. Even in the case of a landing with the noise wheel retracted, the engines will not touch the ground. The improved fuel efficiency of the LEAP-1B engine is due in part to its larger fan. The LEAP's new bypass ratio is 9:1, compared to the 5:1 bypass ratio of the CFM56-7B. The larger bypass ratio is responsible for 50% of the LEAP-1B's gain in fuel efficiency. The LEAP HPC's pressure ratio is now double that of the CFM56-7B. It has increased from 11:1 in the -7B to 22:1 and is responsible for the other 50% gain in fuel savings. The N1 red line on the LEAP remains around 104% N1, but the actual shaft speed has changed. Redline N1 shaft speed for the LEAP is 4,586 RPM, while redline N1 shaft speed for the -7B is 5,382 RPM. In contrast, the N2 redline has been increased to 117.5%, which equates to a mechanical speed of 20,171 RPM, much higher than the 15,183 RPM of the CFM56-7B. During high thrust operation, it is not unusual to see normal N2 indication of more than 100%. And last, the LEAP's EGT red line limit is 1,038 degrees Celsius, compared to the red line limit of 950 degrees Celsius in the CFM56-7B. Technical features. The LEAP-1B engine is made of advanced technologies and innovations. The fan is equipped with 18 woven carbon composite blades. Due to the unique 3D aero design, the blade count of the LEAP is only half that of the CFM56-7B. While lighter and stronger than titanium blades, the carbon composite blades are also very durable relative to bird and FOD ingestion. Aft of the fan, the majority of the air flows into the secondary airflow, where approximately 80% of the engine's thrust is developed. The remainder of the air passing the fan enters the engine's core, becoming the primary airflow. Primary air flows into the three-stage low-pressure compressor, also known as the booster. Between the booster and the high-pressure compressor are the variable bleed valves, or VBVs. The VBVs are designed to avoid stall occurrences in the booster by discharging a portion of the booster's air into the secondary airflow, while the engine is operating at low RPMs or during sudden RPM changes. The VBVs open into the primary airflow and behave like scoops, catching any foreign objects that could have been ingested by the booster and evacuating them into the secondary airflow, bypassing the engine's core. After the 10-stage high-pressure compressor, primary air reaches the combustor. The newly designed combustor improves the mixture of air and fuel, providing a better combustion process compared to the CFM56-7B. This improved fuel-air mixture contributes to the LEAP's overall fuel efficiency. Furthermore, the combustion process is lean, reducing NOx emissions from the engine. After the combustor, the hot exhaust air goes through a two-stage high-pressure turbine, or HPT. The first HPT stage is surrounded by a ceramic composite shroud, and the second HPT stage is surrounded by a cooled metallic shroud. Before leaving the engine, exhaust air passes through a 5-stage low-pressure turbine, or LPT. The LEAP 1B family of engines provides a range of thrust from 23,000 pounds to 28,000 pounds. The only difference between these engines is the delivered thrust. The hardware is the same, but the ID plug is different. The ID plug is an electronic device plugged into the engine's FADEC computer that changes the operating characteristics of the engine, resulting in changes to its maximum thrust output. Engine protections. The engine control is called FADEC for Full Authority Digital Engine Control. Beyond basic engine control, the FADEC also actively protects the aircraft. In case of an N2 engine overspeed, an electronic overspeed system, EOS, independent from the main engine calculator, will command an engine shutdown to prevent it from bursting. In case of an N1 overspeed, the main calculator will detect it and will trigger the EOS, resulting in an engine shutdown as well. Furthermore, to satisfy certification rules, the engine is equipped with a thrust control malfunction accommodation device known as TCMA. In case of an abnormal commanded engine deceleration, to avoid any lateral loss of control due to an excessive thrust dissymmetry, the TCMA will command an engine shutdown on the engine that is not responding normally. This device is only active during takeoff and touchdown phases when on the ground.
New engine features versus flight phases. Pre-flight. On the flight deck, you will find a new engine inboard display unit, new engine start levers, new engine anti-ice panel, and new aft overhead engine panel lights. On the engine parameter display, you will find two new lights. The thrust alert light, which will light up if the thrust is different from the commanded thrust or if the N1 goes above its amber limit. And the fuel flow alert light in case of an abnormally high fuel flow. The engine start levers are equipped with a red light which will illuminate in the event of an engine fire or during an engine fire test. The engine panel is also equipped with new lights. The reverser command light will illuminate if the reverser lever is not down in flight. The reverser air ground light will announce the air ground reverser logic has failed. And the reverser limited light will illuminate in case of an inhibited or idle limited reverser. The engine anti-ice panel is different from the one installed on the NG. All lights are amber. The engine anti-ice light will illuminate if the system is inhibited. The cowl anti-ice light will announce an overpressure condition. And the cowl valve light will illuminate when the cowl valve position disagrees with the switch position. Thus, it will momentarily illuminate when the related switch is moved, indicating a transient condition.